or contractility. End diastolic volume is the major intrinsic automatic factor influencing stroke volume, but stroke volume can also be altered by extrinsic factors. What do I mean by that? Intrinsic means intrinsic to the heart, stuff going on in the heart, Frank Starling. Extrinsic means stuff going on outside of the heart. So, for example, it could be hormones, it could be catecholamines from the sympathetic nervous system. Extrinsic means external to the heart. So, contractility is an increase in contractile strength that is independent of muscle stretch, or independent of Frank Starling mechanism, or independent of preload. And contractility is a direct consequence of a greater calcium influx. We know that the more calcium that's in the cell, the greater the contraction. Where does that calcium come from? It comes from channels, doesn't it? It comes from L-type calcium channels. It comes in, it triggers a release of SR calcium, and that leads to contraction. Over a few beats, if more calcium comes in on that channel, it's going to put more calcium in the SR, isn't it? So the next beat is a little bit more calcium in the cell. And so over a few beats, you can get this increase in calcium and increase in force. There are different things that can affect contractility, and here are some examples. Certain hormones, glucagon, thyroxine, epinephrine, calcium ions per se, and various drugs like digitalis, which is a drug that's sometimes used in failing heart. Digitalis. Positive inotropic. There's a term appeared here. We know inotrope, things that affect contractility, but there are some things that are considered positive inotropes, things that increase the force of contraction, and there are other things that are considered negative inotropes that reduce the force of contraction. So nasty terms really. Positive inotropes, yeah, negative inotropes, things that increase and decrease contractility of the heart. I know, think of strength, think of strong man. I know tropes, things that cause effects on strength, so a negative or a positive effect. And the mechanism is here. So here, imagine this is a myocyte, a cardiac myocyte, contracting cardiac muscle cell. And imagine that catecholamines have arrived, noradrenaline and adrenaline of this cell. We'll see this in real life during the practical. So here we've got a receptor, this thing here, a beta 1 adrenergic receptor. Beta 1, you might say. Well, there are different kinds of adrenergic receptor, and I'll talk about that in a moment, later on. Beta 1, beta 2, alpha, all kinds of different receptors, and they are attached to different mechanisms in the cell. But in this example, you've got a beta 1 adrenergic receptor in the membrane of our cardiac myocyte, that beating cell that I showed you in a dish, contracting away. It's got these beta adrenergic receptors. And when norepinephrine binds to these receptors, so it may be carried in the blood, it may be released from nerve terminals in the heart, yeah? The catecholamine binds to these beta 1 receptors, and what does it do? It increases the activity of an enzyme which you may have heard of called adenylate cyclase. Maybe you've heard of it. Adenylate cyclase, what it does is it converts ATP to cyclic AMP. You may have heard of cyclic AMP being a second messenger, have you, in biochemistry, cyclic AMP. What does cyclic AMP does it converts something called inactive protein kinase to active protein kinase. What does active protein kinase do? Well, it does three things in our cardiac myocytes, at least three things. One of them, it increases calcium coming in on our calcium channels. Remember our L-type calcium channels, plateau phase, brings in calcium. These are our channels. If you increase the open state of these channels, more calcium will come in, won't it? So that's one of the effects, number one. Number two, it increases the calcium uptake by the sarcoplasmic reticulum. So that calcium that's come in here now gets stored away. Okay, so the next time you've got a beat of the heart, there's more calcium in there to be released. And the third thing it does, it enhances the actin and myosin interaction, this protein kinase. So you can see for these three reasons, at the very least, how catecholamines like norepinephrine can increase the force of contraction. When the norepinephrine goes away, this process is reversed. You know, there's no longer cyclic AMP, there's no longer active protein kinase, it becomes inactive. Calcium is no longer stored away, the channel's not bringing in as much calcium, and so on. So, somebody? No, it's okay.
Doctor, can you just a brief, like a minute or two, can you just repeat the whole thing?
Yeah. So, okay, take it one step back even. If we are to go out of this room and run down the stairs, by the time we get to the bottom of the stairs, we'll feel our heart beating faster and stronger. Now, one of the chemicals behind that, if you like, are catecholamines, sympathetics, noradrenaline and adrenaline. So what I'm trying to explain is how noradrenaline or adrenaline, or norepinephrine and epinephrine is the same thing, increase the force of contraction of the heart. So the first thing it does is it binds to adrenergic receptors in the myocyte membrane. In this case, beta-1. Okay? It's called beta-1 adrenergic receptor. And what that does is it activates this process here. It converts ATP to cyclic AMP. Cyclic AMP converts inactive protein kinase to active protein kinase. Active protein kinase opens calcium channels, so more calcium comes in. It increases the uptake of calcium, remember the SR calcium pump? It increases the calcium uptake by the SR, and it also increases the actin and myosin interaction. So all these things together, they're going to lead to an increase in the force of contraction of the cell, of many cells of the heart itself. Yeah? Okay. So what do we know about catecholamines in general? Sympathetic stimulation. We know heart rate goes up and force of contraction goes up. I haven't explained yet how the heart rate goes up, I will. But here's our normal, 75 mils, 75, 250, our normal resting cardiac output. When there's sympathetic stimulation around, what I'll explain just now is the stroke volume will go up, won't it? The force of contraction will go up. We know intuitively that the heart rate goes up, but you don't know the mechanism yet. If they both go up, of course you're going to increase the cardiac output, aren't you? Yeah? The thing you don't know on here at the moment is how the heart rate increases. Exercise, I mean that's a sympathetic thing, isn't it? It's the same. Fear, fight, flight. You're running, it's an exercise thing. And we know that when we run, our heart rate goes up, our stroke volume goes up, our cardiac output goes up. And now we know at least the mechanism behind this, catecholamines, cyclic AMP, protein kinase, and those three different mechanisms. We need to know more about heart rate. Okay, so we've talked about preload, we've talked about inotropy or contractility, which is anything that affects the force of contraction other than preload, other than Frank-Starling, which is an intrinsic mechanism. The final thing is afterload, and basically this is the back pressure exerted by arterial blood afterload, after the heart, that must be overcome for the ventricles to eject blood from the heart. So clearly, as the afterload increases more and more and more, for example, pathophysiological hypertrophy, the heart has got to work harder and harder and harder, hasn't it, to move blood out. So that's the idea of afterload. Preload, afterload, contractility. Those are the three things that we've talked about. So this is a little diagram here that's showing that it becomes more and more difficult to pump blood out. You know, if the pressure, let's say in the aorta, increases more and more, isn't it? So this is showing left ventricle trying to move blood through the aortic valve into the aorta. If the pressure in the aorta goes up higher and higher and higher, the left ventricle has to work harder and harder and harder, doesn't it? To create a pressure gradient to open the aortic valve to move blood, isn't it? Yeah? Okay. So the last part of the is the heart rate. And what we know is that activation of the sympathetic nervous system, for example by emotional or physical stressors, loosely called fear, fight and fright stimuli, stimulates the sympathetic nerves. They release noradrenaline or norepinephrine. Also stimulates the adrenal gland, by the way, that produces adrenaline or epinephrine. And these things will affect the heart. Sympathetic stimulation increases the heart rate. Yeah, remember that. Sympathetic stimulation increases the heart rate. Parasympathetic stimulation reduces the heart rate. Yeah? Sympathetic stimulation also increases contractility. We've just seen it, haven't we? Okay, so this is an important point here. Vagal innervation of the ventricles, in other words, parasympathetic. Vagal is parasympathetic, vagal is acetylcholine. Vagal innervation of the ventricles is sparse, not much of it. So parasympathetic nervous system activity has little effect on force of contraction. So in summary, what you can say is that sympathetics affect force and rate. We know that when we run. We feel the heart beating faster and more forcefully. However, parasympathetic affect the rate, yes, they slow the heart down just when we go to sleep or when we relax. But they don't have much effect on the force of contraction. Why? Because there's not much innervation of the muscle. There's innervation of the sinoatrial node and the conduction machinery, but there's not much innervation of the ventricles. Okay? Sympathetic, force and rate, parasympathetic, rate, mainly. So, at rest in this room now, both autonomic divisions of the nervous system, parasympathetic and sympathetic, send impulses to the sinoatrial node. But the dominant influence is inhibitory. So in this room right now, you have the sympathetic innervating your sinoatrial node, you have the parasympathetic innervating the sinoatrial node. The sympathetic increases rate, the parasympathetic reduces. But the dominant one is the parasympathetic, the vagal nerve. If I was to cut that vagal nerve, what would happen? The heart would be? Faster, yeah, that's right. So that's why when I use the word dominant, so if the parasympathetic is dominant at rest, if I cut that, and the heart rate would increase, that's evidence for the dominant effect, isn't it? Yeah.
Sorry, Doctor, but can you put that sentence again? I couldn't connect to that.
Yeah. Got it? Yeah? Okay. So, under resting conditions, both autonomic divisions continuously send impulses to the sinoatrial nerve. But the dominant influence is inhibitory. The heart is said to exhibit vagal tone, and the heart rate is generally slower than it would be if the vagal nerve wasn't innervating it. Cutting the vagal nerves results in an almost immediate increase in heart rate, reflecting the inherent rate of about 100 beats per minute of the pacemaking sinoatrial nerve. In other words, if you cut the vagus nerve to the heart rate will increase. The numbers don't matter. It's indicating that the vagal nerve, the parasympathetic, has a dominant effect at rest. So sensory input from a variety of sources regulates the activity of the sympathetic or parasympathetic divisions of the autonomic nervous system. In other words, it's not always the same. When we run, the sympathetic becomes dominant. When we fall asleep, the parasympathetic becomes dominant. It's a balancing act between the two, yeah, that controls the heart rate. How does it do that? You remember this little diagram? Okay. This little diagram shows the sinoatrial node, doesn't it? Remember that? Important here is the pacemaker, the slope, if you like. This is the depolarization. Remember, it's L-type calcium current. And this is the depolarization, various potassium conductances. You can see that all kinds of things are involved in this pacemaker or slope. I-cal or L-type, T-type, IF, the funny current, sodium current, yeah? All kinds of things are involved in that slope. So clearly, if that slope changes, yeah, if this becomes steeper, it's going to reach threshold sooner, isn't it? If this slope becomes shallower, it's going to take longer to get to threshold. So if you fiddle with the slope, you fiddle with the rate. The question is, how's the fiddling done? And here we can see, this is a control. Look at the red bit here, slope. Here we've got sympathetic effect. Notice the slope now is becoming much steeper, isn't it? So you're getting more action potentials per unit time. Parasympathetic, notice what's happening. This is becoming much shallower, isn't it? So it takes longer to reach threshold. And so, the rate goes down. So I'm going to stop there, and we'll continue next time because it's coffee break, I think, to show you the mechanisms involved in this slope change, if you like, and hence rate. Is that okay? Yeah? So I'll be back with you in one.